Welcome, everyone. Let's begin our lesson for today by going over the learning goals and success criteria. First, what are we learning? We're learning how to determine whether a function is even, odd, or neither, how to determine whether or not a function is closed, and how to determine the end behaviors of a function, and how to compose multiple functions. How are we learning it? Through the Reasoning with Features of Functions Part 2 notes and the Reasoning with Features of Functions Review Part 2 assignment. When can we use this information? To recognize trends and graphs to determine the trends in the stock market, to perform simple calculations such as a budget by recognizing boundaries of numbers, to determine if adding the items in your budget will stay within your income amount, to determine the direction a stock is trending and to determine if we can anticipate that trend continuing, and to determine how a given stock might change if the market trends change. How do we know we learned it? By getting a score of 4 on the Reasoning with Features of Functions Review Part 2 assignment. Now let's take a look at our agenda for today. We will begin by going over the learning goals and success criteria. While we do that, you'll fill out your Get It Started. Once you've completed your Get It Started, we'll go over it together and answer any questions that you may have. After that, we'll go over the Reasoning with Features of Functions Review Part 2 notes, and then I'll give you time to complete the Reasoning with Features of Functions Review Part 2 assignment. Once you've completed the assignment, we'll go over it together and answer any questions that you may have. At the end of class, we'll go back over our learning goals and success criteria while you fill out your Before You Go. Your only homework for tonight is to continue working on the Reasoning with Features of Functions study guide and any incomplete assignments that you may have. Let's take a look now at the Reasoning with Features of Functions Review Part 2 notes. The notes begin with the learning goals and success criteria. So what is an even function and an odd function? An even function is a function that is exactly the same for f of x and f of negative x. So what this really means is that even functions are symmetric across the y-axis. So if I look on each side of the y-axis, I should see a direct reflection or a mirror of the function. So they are reflected across the y-axis. Now an odd function is exactly the same for negative f of x and f of negative x. And what this means is they are symmetric across the origin, meaning that they are rotated 180 degrees about the origin. So what does this really look like? Well, I have an even function here, and if I look at just this side, on this side of the y-axis, if I were to take that and flip it over, it becomes this part here. So every point, if I reflected it across this axis, it would be directly where it needs to be. So this is an even function. Now an odd function is something that's rotated. So I spin it 180 degrees. If I take this point here and spin it 180 degrees, it should end up right there. If I take this point and spin it 180 degrees, it should end up right here, and so on. So the whole function is spun around the origin. So this is an odd function. Now, neither functions are just functions that are neither even nor odd. They're not reflected and they're not rotated 180 degrees.
Now let's talk about the definition of infinite set closure. First of all, what does infinite mean? Infinite means an uncountable number of elements. So it goes on to infinity. It keeps going forever. So an example of this would be like the natural numbers. So we can count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and we can keep counting. And no matter what number we stop at, there's always a number past it. So that's an infinite number of elements. Therefore, an infinite set means that we cannot count the number of elements in the set. The opposite of this would be a finite set in which there are a countable number of elements. So let's say I wanted the natural numbers between 1 and 10. Well, that goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 and stops. And we can't keep going. So that would be a finite set. So an example of an infinite set would be the set of integers. So there's no limit to the number of integers we can count. Now, closure definition. What does closure mean? Closure under an operation means a set is considered to be closed if when that operation is performed on any two elements within the set, the result is also in the set. Okay, note that this must be true for all elements in the set. If there is even one case where the result falls outside the set, then it is considered to be not closed. Okay, so let's take a look at what this means. So here's an example. We have the set of -1, 0, and 1, and want to know, is it closed under addition? So what that means is I'm going to take each of these elements, so like -1 and 1, and when I add them together, I get 0, which is in the set. So that means that the set might be closed. If for some reason though I end up adding two numbers together and the result is outside the set, so let's say I add something together and I get 6. Well, 6 is not in the set, so therefore it is not closed. So an example of what would make the set closed would be -1 plus 1 equals 0. Because 0 is in the set, it looks like it might be closed. Now, is there an example we can come up with that makes it out of the set? Well, if we add 1 plus 1, because we do need to include it plus itself, so 1 plus 1 equals 2. Well, 2 is not in the set, therefore the set is not closed. And again, if there's even one example of this, so it doesn't matter that this part ended up inside the set. Because this one example is out of the set, then the whole set is not closed. So now let's take a look at this infinite set here, the set S of integers, and what we want to know is it closed under addition. Now we can't use a table anymore, so we need to think of some examples of addition of integers and then try to broaden it and say, is there any way that any two integers can be added together and not be an integer? So we do some examples here, and we can see that they're still turning out to be integers. So is there any way we can add two integers together and not get an integer? So if I add any two negative integers, is there any way to get a fraction out of it? Is there any way to get a real number out of it? Is there any way to get a complex number out of it? Well, no, there's not, right? Anytime I add any two whole numbers together, I should get another whole number. So therefore, there is no way to add two integers together without getting another integer, so therefore the set is closed. Now what about this? The set S of integers closed under division. So again, we're going to think of some examples. So we have 2 divided by 1, 1 divided by 2. Notice here though, when we do 1 divided by 2, we get 1/2. Well, 1/2 is not an integer, that's a rational number. So therefore, when we do it that way, we know that it's not closed. Now, there's an easier way for us to be able to tell that this set is not closed. Because I told you last time, if we include 0 in the set, then it is never closed under division because it's undefined. So if we divide something by 0, it will always be undefined. So 0 is an integer, so if we were to divide a set by 0, it would be undefined. So therefore, that previous set would not be closed because of division by 0. Now, what if we said the set of rationals excluding 0 is closed under division? Well, again, we're going to think of some examples. So we have 1/2 divided by 1/4 is equal to 2, and -1/2 divided by 1/3. Remember, really, it's just multiplying by the reciprocal. So is there any way we're going to get something other than a rational number, other than a fraction? Well, we keep thinking of some examples, and when we keep looking, we can see that there is no way, and we did exclude 0, so we know that 0 is not an issue, so we don't have to worry about dividing by 0. So therefore, we can just look at these examples and continue to come up with more examples, and we can see that the set is actually closed because no matter what, when I divide two fractions by each other, I will always get another fraction.
Now there's a video here that shows you how you can use a spreadsheet to find values that you'll need for your assignment for today. So go ahead and watch that video. Let's take a look now at how we can use a spreadsheet to solve math problems. So we're going to use Google Sheets here, and this is for the compositions of functions part 2 assignment. Notice the formulas are already placed in here, so all you have to do is copy and paste them. So I'm going to go ahead and copy this, and then go down one and put equals, and then paste it. Then I hit enter. Notice it placed the answer there, and then asks if I want to autofill. I'm going to go ahead and put the check mark. That autofills these. Now I do it again for this one. So I copy this, equals, and paste it. Hit enter, and then autofill. Do it again. Copy this one, equals, paste it, check mark there, and then the last column here we'll do the same thing, copy, equals, and paste it. It asks if we want to autofill, yes we do, And this will be your answer column here. This will be the column that you're using. So you'll put these values into your Desmos activity from here. Then once you're done with this one, you'll go to the next tab, which is here at the bottom, and do the exact same thing. So you'll copy this, equals, and paste, and then autofill. And you'll do that for each of the columns. Then you'll go on to 2C, do the same thing here, and place those values into your Desmos activity. So this is how you can use a spreadsheet to help you with your math problems. Now, what is end behavior? End behavior is the behavior of the graph as it approaches positive infinity or negative infinity. So end behavior can be written as this: as x approaches some value, and it doesn't always have to be infinity or negative infinity. It could be some value. It could be the asymptote. So as it approaches, and this negative sign means that it's approaching from the left side. So as it gets close to that point from the left side, y is approaching some value. The other version would be as x approaches that point from the right side, then y is approaching something. So an example of this would be here. So we have our function here, and we have a vertical asymptote here at -2. So we're going to say then, as x approaches -2 from the left side, what is y doing? Well, as we get closer to -2 from the left side, we can see that y is increasing exponentially. So y is approaching infinity. So as x approaches -2 from the left side, y is approaching infinity. Now, if we look at as x approaches -2 from the positive side, so from here, so from the right side, so as we get closer to -2, what is happening with the graph? Well, we can see it's going up and up and up, so y is also approaching infinity. This is how we can describe end behaviors. Now, let's take a look at some end behavior descriptions. So when asked what the end behavior is on the left side of the graph, the question is asking for the end behavior as x starts to approach some value from the left. And likewise, when it asks for the right side, it's asking for as x approaches some value on the right side, what is the graph doing? So in this case, we're looking at as x approaches negative infinity, what is y approaching? And as x approaches infinity, what is y approaching? So for instance, this is an example we did already, and we looked at -2 as our end behavior, but what about as the graph goes to negative infinity? So as x approaches negative infinity, y is approaching, and notice it's getting flatter here. It's approaching some value here, which we don't know. So we'll just call it b for now, and we know that b is smaller than 0, right? Because it's some number under the x-axis. So the y value is approaching some value here, b. Now, same thing on the right side. So as we approach infinity, as we keep going to the right, we're getting flat as well, approaching some value b, where b is the same thing as on the other side, and it is also less than 0. Now, what is the degree and lead coefficient? The degree is the highest power of a term or variable. So for instance, x squared. If squared is the highest exponent that exists, then we would say that's the degree. So for instance, we have y equals 2x squared plus 3x minus 2. Well, the highest exponent that exists here is 2, so we would say it has a degree of 2. Now, the lead coefficient is the number in front of the highest exponent. So in this case, my lead coefficient is the number in front of the x squared term, which is 2. So my lead coefficient is 2. Now, what is an asymptote and a hole? An asymptote is a line that the graph approaches but never crosses. So an example of this would be 1 over x minus 1. And we can say that it has an asymptote at x equals 1. Because anytime the denominator equals 0, that's a spot where it would be undefined, because now we're dividing by 0. And remember from closure, if anytime we divide by 0, we have an undefined value. So it's undefined at this point, so we create an asymptote there. Now, a hole is a point that is not on the graph, and because it can be factored out of both the top and bottom. So it's where the graph continues on and then stops for a second and then continues on after that. So an example of this would be x plus 1 over x plus 1 times x minus 1. And we'd say it has a hole at x equals negative 1, because this can be factored out of both the top and bottom. And then we would solve that for x, and we get x equals negative 1. Now, what is a horizontal asymptote? A horizontal asymptote is a horizontal line now, which means it goes side to side, that the graph approaches but never crosses. Horizontal asymptotes occur when the equation for a function has a denominator that is a higher or equal degree of the numerator. So for instance, 3x plus 1 over x minus 2. Well, notice they're both degree 1, so if they're the same or the denominator has a higher degree, then we're going to end up with a horizontal asymptote. Another example would be x minus 1 over 2x squared plus 7. Well, we can see that there's a higher degree down here, so we're going to have a horizontal asymptote. So how do we find the horizontal asymptote? If the numerator and denominator have the same degree, the horizontal asymptote is the numerator divided by the denominator. So for instance, 3x plus 1 over x minus 2. So we take the lead coefficients, 3 over 1 equals 3. So we're going to have a horizontal asymptote at y equals 3. Now, if the degree is not the same, so the degree in the denominator is bigger, we're going to have a horizontal asymptote at y equals 0. So for instance, x minus 1 over 2x squared plus 7. Well, we can see that we have a higher degree in the denominator, so we're going to have a horizontal asymptote at y equals 0. Let's take a look now at the reasoning with features of functions review part 2 assignment. The assignment begins with the learning goals and success criteria. If we scroll down, we can see the questions. It says, what is the sum or adding of the two functions below? y1 equals x minus 1 and y2 equals 3 over x plus 1. Well, if we add these two together, we get x minus 1 plus 3 over x plus 1. If we multiply both top and bottom by x plus 1, so we need to multiply this part by x plus 1 to have a common denominator. And when we do that, we get x squared minus 1. So we get x squared minus 1 plus 3, which is x squared plus 2 over x plus 1, which is this one here. Then we look at the next question. It says, what happens to the values of the function below as x approaches infinity? So as x gets really large, what's happening? Well, as x gets really big, that means that it's getting closer and closer to 0, because 3 over a very large number becomes a very small fraction. So that means it gets smaller and approaches 0, which is this one here. And we'll continue to answer these questions all the way until we get to the end. When you get to the end, go ahead and click Next. This will take you to your Before You Go. Go ahead and fill out your Before You Go and then submit your work on Google Classroom.